Good morning, everybody. We are continuing our discussion of CPU designing, and in the last few classes we already discussed the concept of instruction cycle, machine cycle and state, and we told that CPU is nothing but a state machine. It's called a state machine, and we already in the last day we already seen how the different smaller operations will be done in every state, that's mean in a clock pulse of an CPU, and that is called the register transfer level instruction. So RTL, that is called the register transfer level. This is the basic activity done within the CPU, and today we will see how this RTL register transfer level instruction is organized, and to understand the RTL we'll understand the organization of the CPU. Within the CPU what happens and how these things is done, we'll see those things. Here let us see, suppose this is a machine cycle. We know that a machine cycle is consist of multiple clock pulse, and every clock pulse is called a state. So suppose this machine cycle is consist of 4 state. So this is T1, T2, T3, T4. These are 4 clock pulse, as well as this is called 4th state. So now this is your memory. From the memory, within the memory, the instruction will be stored, and from the memory, before execution, CPU have to fetch the instruction, and then it have to execute the instruction. So one instruction fetch operation that consists of one machine cycle can be divided into 4 different states. So all these are the different states. So let's see. Last day we already seen the basic operations of 4 states. We already discussed that thing. What was the first state? This is the first state. That's mean first state will be executed in the first clock pulse. Then what will happen? CPU will generate the address, and that address actually within the CPU. This is the CPU. Within the CPU, that address will be stored in a register. That register is called address register. So from the address register, the particular address will be put on the bus. So that's why the first state we written like that, address that will be put on bus. What type of bus? This is the address bus. The address part of the bus will be, this address will be put on bus, and this is called this is one CPU activity. Clear? So this way, from this address register, this address will be put on the bus, and then within the memory it will be decoded, and then it will find that particular locations. All these are the different locations of the memory, and within every location there will be instruction will be stored or data will be stored. Here suppose this data means this is the instruction that CPU wants to access, so we indicate that by data. So suppose your required instruction is stored here, and that address will be decoded, and you will find out the instruction in this location. Now in the second stage, within the CPU we know that there is a controller. So controller generate the control signals. So I know that we already learned that here the important control signal that will be generated by the CPU, that is a read operation. That means it will be read from the memory. So this read operation will, so the next state will be read. It's the control signal. It will be generated by CPU, will be put on the bus, and the control part of the bus, it will be put on the control part of the bus. So here read signal will be put on the bus. So then that will be goes to the controller of the memory. This is the controller of the memory. So this is the memory section. Within the memory there also be a controller. So this read signal will be go there. Okay. So that's mean whatever the data is present within this location, that should be placed into the bus. So in the next state or next clock pulse, what will happen? The data, that's mean the instruction. So that's why we written data dot instruction. That's mean your record instruction will be put on bus. So that's mean this data will be put on bus. So here we can see that within the same bus there are 3 different sections. One is address bus, control bus and data bus. So this data will be put on the data bus. So this will be the third state. Then in the fourth state, what will happen? This data is present within the bus. So this data will be stored within some register that is called instruction register. As we are fetching an instruction, that's why the register that hold this instruction, that is called the instruction register. But if we fetch the data, then that data can be placed in another register, that may be data register, because within the CPU there are so many registers. So here, as we are fetching the instruction, that's why the register that hold this instruction, we mentioned that register as instruction register. So required data will be stored in the instruction register. That things will be written here in the form of RTL register transfer level instruction. So that is data that is present within the bus, that will be put on where it will be placed on instruction register. So basically this 4 state will be executed within a machine cycle. That means for fetching an instruction, these 4 steps will be done in 4 clock pulse, and these are called the register transfer level instruction. Now let's see. We know that CPU is called the state machine. Now how these states will be done here? So look at here. CPU generate the address, and from the memory we access the data. But the speed of the CPU and speed of the memory cannot be equal, and basically most of the cases the speed of the CPU will be greater than the speed of the memory. So suppose for say memory access time is, so suppose consider memory access time equals to 200 nanosecond. Suppose memory access time is 200 nanosecond. Clear? And suppose CPU clock is 100 nanosecond. So that means CPU is twice faster than the memory access. So in this case, what will happen? In this case, so suppose in the first clock pulse, this first operation will be done. That means the first state will be executed. In the second clock pulse, the second state will be executed. So that means second state means you are putting the control signal, read control signal to the memory. Now from the memory the data will be passed to the bus. So this third state, this will take more than 1 clock pulse. It may take more than 1 clock pulse. Here we are considering that everything is done in every 1 clock pulse, but here in this situation the memory access time is slower than the CPU clock pulse. So that's why this data will be accessed in more than 1 clock pulse. So suppose, so this is our first clock pulse. So this is our second clock pulse. This is our second clock pulse T2. In the third clock pulse, what will happen? In the third clock pulse, it will be a waiting state. So you can say it is the TW. It's called the waiting state, because it can take more than 1 clock pulse. So that's why after 2 clock pulse, one will be waiting clock pulse, and then there will be T3 clock pulse. So it will be new T3. So that's why T3 dash. So this is the third clock pulse. So that's mean in between second and third clock pulse there becomes a waiting state. Why? Because memory is slower than the CPU. We are considering that memory access time is slower than the CPU access time. Then the fourth clock pulse T4 will be accessed, and this way the remaining part will be done. Okay, so this is called the waiting state. So this way we can say that every time these things cannot be happen, sometime this type of waiting state can be introduced in between some state. Clear? Now we will see why CPU is called the state machine. So we know that CPU is called the state machine. So let's see how these things is done within the CPU. So CPU is called state machine. CPU is called the state machine. Clear? So now if we draw the SM chart, if you draw the flow chart of these states, then it's like when you study the flow chart, so it will be like flow chart of the program, but there is a slight difference in between the normal flow chart and this flow chart. So that's why it is called the ASM chart. ASM chart. So A for algorithmic state machine chart. If we draw the flow chart of these states, then it is called the algorithmic state machine chart, not the flow chart. It is called the algorithmic state machine chart. In short form, it is called the ASM chart. So let's see an example of an ASM chart. So how we can draw the ASM chart of this particular states. Okay. So here the first state is T1. First state is T1, and the output of this first state, this is the output of the first state. So what will be the output of the first state? Address will be put on the bus. So it, in short form, we can write address will be put on the bus. Address will be put on the bus. This is the first state. In the second state, what will happen? In the second state, what will happen? The control signal will be put on the bus. So the read control signal will be put on the bus. So this will be in the second clock pulse. In the third clock pulse, it will check the ready state. So that's mean whether this signal is ready or not. We know that what I told you, that to fetch the data, it can take more than one clock pulse. So that's why when RD signal will be on, that's mean it will be ready to fetch the data. If RD is 0, then that's mean it have to wait. That's mean you have to introduce a waiting state here. So that's why we will check the ready state, whether it is 0 or 1. So if it is 1, then what will happen? We'll move to the third state. This is the state 3, third state. What is the third state? In the third state, the data will be put on the bus from the memory, and if it is the 0, then it will go to the waiting state. It will be go into waiting state. You can say TW. It is the waiting state. There nothing will be done here. Okay. So from this waiting state, it will be check the ready signal. If ready signal is 0, then it will be moved to this another ready state. Another waiting state will be there. If it is 1, then what will happen? It will be moved to this position, and then it will be moved to the fourth state. That's mean it will be the data will be put on the instruction register. So data will be put on the instruction register. And so if we draw all these states in this chart form, flow chart form, then it's called the ASM chart. That's mean algorithmic state machine chart. Clear? So now from here we can understand a very basic concepts of the CPU designing. So suppose you have a particular CPU, and this particular CPU will have a particular set of instructions. So this is a flow chart or ASM chart of a particular machine cycle, We know that instruction cycle. So if there are a set of instructions of the CPU, then there will be lot of instruction cycle, and instruction cycles will be divided into different machine cycles. So this is one example of a machine cycle of one instruction, and this is the flow chart of these things. So now if you take the whole set of the instruction, then you can draw this kind of set of flow chart, that's ASM chart of this particular instruction. Actually that is the characteristics of the CPU, and this kind of statement is called micro instruction. This kind of instruction is called micro instruction. So this kind of instructions also called micro instruction. Micro instruction. So if somebody can write down the micro instruction, that is called the micro programmer. But we should remember that this micro instruction, in normal cases we cannot write down our micro instruction, because if we can write the micro instruction, that means we will change the characteristics of the CPU. But most of the CPU you cannot write down the micro instruction, but there are so many CPUs, they are called the micro instruction CPU. So that means on those CPU you can change the features of the instruction features of the CPU, but in most of the cases you cannot write that. So these micro instructions, so from, if you take the whole instruction set of the CPU, then you have a set of micro instruction level, and that is called the characteristics of an instruction. And this micro instruction will be generated by the different control signals generated by the CPU. And to understand how these micro signals will be, actually whole micro signals will be generated, we have to understand the register architecture, the register architecture within the CPU. That's when we have to evolve the internal architecture of the CPU again. So from the basic level we come into this level, and now we enter into the another depth. That's when we will elaborate this architecture further to understand how the different micro instructions will be, or microcontroller will be generated. And that's why we have to study the data path. That's mean the whole structure of the within the CPU, how different registers are there, how they are interconnected, and that is called the data path. So that is called the data path of CPU. So in the next class we will discuss the data path of the CPU. Okay, thank you.